Assalamualaikum warahmatullahi taala wabarakatuh. And today we from group D will present about the application of differentiation on MAT183. So this is our group member, which is me, Muhammad Zurakimi, and we have Muhammad Irfan Haziq, Muhammad Ilham, Ahmad Nazrin, and lastly Muhammad Akril Ilham. So today we will discuss about firstly the introduction, and then we have our problem statement, and then there's the problem solution, and also finally which is the conclusion. So for introduction, in calculus, differentiation is one of the two important concepts apart from integration. Differentiation is a method of finding the derivative of a function. Differentiation can be defined as a derivative of a function with respect to an independent variable. Differentiation in calculus can be applied to measure the function per unit change in the independent of variable. For related rates. Related rates and problems involving related rates take advantage of quantities that are related to each other. Related rates help us determine how fast or how slow a certain quantity is changing using the rate of change of the second quantity. In application of differentiation, selecting related rate is essential since it helps us examine and comprehend how various variables vary over time. Because of this, related rates are a useful tool for modeling dynamic systems in real-world scenarios where quantities are linked and their rates of change affect one another.
Problem statement. First problem is a block of ice in the shape of a cube is melting in such a way that the length of each of its edges is decreasing at the rate of 2 cm per hour. At what rate is its surface area decreasing at the time its volume is 54 cm cube? Assume that the block of ice maintains its cubical shape. Second question is, let theta in radian be an acute angle in a right triangle. X and Y are the length of the side adjacent and the opposite to theta respectively. Assume that X and Y vary with time. A. Show that dy per dt equal to dx per dt tan theta plus x set square theta d theta per dt. B. At a certain instance, x equal to 4 meter and is increasing at 1 meter per second while y equal to 4 meter and is decreasing at 0.6 meter per second. How fast is theta changing at the instance? Is theta increasing or decreasing at the instant?
First question. With the question given the length of the each edges with decreasing rate, so the dLdt is equal to -2 and its given volume is 64. By using the volume formula, we can get the actual length of 4 cm. By using the surface area formula, we get 6L square. By differentiating it, we get dl to get 12L. When the L is equal to 4, then substitute it into 12L to get 48. So to find the rate of the surface area, which is dSA dt, is dSA dt equal to dSA dl times dl dt. By using all the work into the equation as this dSA dt equal to 48 times -2 is equal to negative 98. And let's move on to the next question.
So for the second question, let theta in radian be acute angle in a right triangle. X and Y are length of the side adjacent and opposite to theta respectively. Assume that X and Y vary with time. So for the A, they give us the equation. So from the equation, we just put X on the one side and the Y on one side. So the answer is X tan theta equal to Y. And then for the B, the question show that the info is X equal to 4 meter and increasing at 1 meter second, and while Y equal to 4 meter and decreasing at 0.6 millisecond. And how fast is the theta changing at that instant? So from this question, we just take that we just take the equation from the previous question, and we just put that info from the question, and we will get the answer is d theta equal d theta per dt equal to negative 1 per 5 rads. Therefore, theta is decreasing at rate of negative 1 per 5 radius.
Conclusion: In summary, differentiation is a fundamental concept in calculus that enables us to determine the rate of change of functions. It allows us to find the derivative, a measure of a function's instantaneous rate of change, with respect to its input. Understanding differentiation conceptually and mastering associated skills open up countless useful applications. We can analyze properties of functions, optimize parameters, model real-world phenomena involving motion, formulate predictions, and so much more by leveraging derivatives. Powerful differentiation rules and techniques make finding derivatives systematic and convenient even for complex functions. Overall, differentiation equips us with an extremely valuable mathematical tool to probe rates of change. A grasp of what derivatives represent and how to find them helps unravel the workings of process underpinning much of science, nature, and everyday life. The profound utility of differentiation explains to its central role within the calculus framework.
Thank you.